We now want to consider what happens when we have two random variables that may or may not depend on one another. So instead of dealing with a probability density like we did for the case with one random variable, we're now going to deal with a joint probability density when we deal with two or more random variables. And we're going to write that probability density as p as a function of x and y. And this joint probability density is going to be defined in such a way that p of x and y, dx dy, is going to be the probability that random variables 1 and 2 have values between x and x plus dx, and y plus dy, respectively. So variable 1 has to fall between x and x plus dx. Variable 2 has to fall between y and y plus dy. We can visualize that joint probability density by imagining a three-dimensional plot where the axes are x, y, and then that joint probability density. So suppose we have some peak in our joint probability density. Well, the most likely place to find x and y would be at these values of x and y. If I were to visualize that as a contour plot, we can see there's a peak right here in our joint probability density. However, the probability of finding any value x and y, or finding variables x and y in any range of values, can just be visualized by picking a range of x values, picking a range of y values, and then selecting the region within that range. The probability of finding x and y both within that range is then just going to be the area under that joint probability density curve. Okay, so all we have to do to find the probability is just within some range is just integrate up a bunch of these tiny differential areas. Just as with functions that have one random variable, we're looking at multiple random variables, joint probability density here. If I have a joint probability density, we still have the convention that the total probability has to add up to 1. So if I add up all of the area underneath my joint probability density curve, or to put that another way, I take a double integral over dx and dy over the complete range of possible values. That has to equal 1 by convention because we are defining the total probability to equal 1. Again, that's just called normalization. Suppose I want to compute the average of some function, or the mean of some function. Suppose I'm looking at some function of those two random variables. Well, it works very similar with a joint probability density as it did with just a single variable probability density. If I take an average, I'm just going to use the angle brackets to denote that average. And just like we did before, we are going to take that function times the probability density, in this case the joint probability density, and then we are going to integrate over the full range of that function. So in this case, it's a two-dimensional integral. It'll be over dx and dy. And we'll also make sure that we cover the full range from minus infinity to infinity over both the x and y integrations. Okay, so I've got double integral for function times the joint probability density integrating over dx and dy. At this point, it's helpful to have an example illustrating what we mean by joint probability density. So suppose I choose a person at random and I measure their height and weight. What's the probability that I am going to get a certain height and a certain weight? Well, I can plot that probability, the probability that I have a height, a certain height and a certain weight, as a probability density in a three-dimensional plot where on the x-axis we have the height, on the y-axis we have the weight, And on the z-axis we have that probability density, that joint probability density. However, it's going to be very difficult to plot that on a three-dimensional plot, so I'm going to try to show this as a contour plot. So you might suspect that as your height gets bigger, you are more likely to have a bigger weight. Therefore, that point you would expect is going to be fairly large. If I'm way on the high end of my height graph, you would expect to be way on the high end of your weight graph. In contrast, you would expect at this point, being very tall or having a large amount of weight would not correspond to being very short. So if you are 3 feet tall, you're probably not going to weigh 600 pounds. Similarly, if you are 7 feet tall, you are probably not going to weigh 50 pounds. So the most probable events in this graph are going to be centered along some line that just relates height and weight. And as you get further away, you will get less and less likely. So this inner plot has a high probability, and as you get further and further away, you get lower and lower probabilities because you expect the height to correlate with the weight that you have, at least to a certain degree. Some short people will weigh more, some tall people will be very skinny and weigh less, but on average you would expect there to be some correlation between height and weight. Suppose we want the probability density for a single variable, for a single random variable, and I want to get that from the joint probability density. So we're starting with a joint probability density for x and y, those two variables together. What if I want to condense that to just worrying about the probability density for x? Well, there's an easy way to do that. All we have to do is integrate over all the possible y values. So if I want to get the probability of x for any possible y, so in some sense regardless of y, all I have to do is integrate out that y dependence over all its possible values. And this will give me the probability density for x irrespective of what y happens to be. So we can go from a single probability density, or from the joint probability density to a single probability density just by integrating out one of the variables. Similarly, if I wanted p of y, I would do the same thing, except I would integrate over dx instead. Sticking with our height and weight analogy, we can say that height is correlated with weight, but suppose I don't care what weight I'm looking for. All I care about is what's the average height of a person. Then what we can do is I can look here. If all I care about is height and not weight, I can integrate over all the different possible weights to find the most probable height. So basically what I'm trying to do is condense this contour plot to be a plot just of height alone. So we could take the probability of having some height h. I can find that from that joint probability density. I can find the probability density of just the height. Then you might get something that looks like this. Maybe there's some peak around 5 foot 7 inches. Okay. Well, we get that. We get that probability of being a certain height. Again, just by integrating over all of the possible weight values. So all I'm doing is adding up all of the different possible weights I can be and their respective contributions to the joint probability density. And when I do that, again, we just express that as an integral. So I would integrate the joint probability density of having a certain height and a certain weight. I would add it up for all the different possible weights. Another way to put that is we're integrating out the weight variable so that we are left with just a function of the height. So this would tell me what the probability is of having a certain height, regardless of what weight the person happens to be. Suppose we want the probability density for a certain variable, a single variable, given that there's a particular value for some other variable. So suppose we want to find the probability density for x, given that I know y has a certain value. Well, we can do that. We're going to express that in this way. We're going to define, we're going to use this notation. P of x, straight line down, given y, we read this as probability of x given y, dx, that's going to be the probability of finding variable number 1 between x and x plus dx, given that variable 2 is equal to y. So we can find this. We call this conditional probability because it depends on the condition that y has some certain value. Again, sticking with our height and weight probability analogy, let's see what happens if I want to know the probability of having a certain height, given that we know a person has a certain weight. So suppose I know a person has a weight of 150 pounds. So I know their weight falls somewhere on that line. Well, I can tell, just by looking at this plot, that the person is most likely to have a height that's right in the middle, where we have a maximum. We have some height that correlates with that weight, and as you get taller, the probability of having that weight goes down, or that height goes down, the probability of having a shorter height goes down as well. So we can condense this plot to the probability of having a certain height given a weight of 150 pounds. And all I'm really doing is taking that slice of the graph. You find what's the maximum probability of having, or probability density of getting a certain height, given that we have a weight of 150 pounds. Maybe a weight of 150 pounds correlates with a height of 5'7" inches. If that's the case, I'm making up numbers here, I have not looked these up. But how do we actually get this function, this probability for having a certain height, given that the weight has some particular value? How can I find that from the joint probability density? So we would like to know what's the probability of getting a certain height given that we have a certain weight. The fact that we are given some information about the problem gives us a condition on it. We call this the conditional probability. We write that as P of x given y. And how can we relate that to the joint probability density? Note that these are different. Here I have a straight line up and down. This is just a comma. How can I relate these two things? Well, it turns out we can relate them by something called Bayes' theorem. This is called Bayes' theorem, which says that the probability of getting a value x, given that you know you have a value y for the second random variable, is equal to the joint probability density of x and y divided by the probability density of getting y by itself. This is known as Bayes' theorem. It is it is the most important thing in conditional probability. It's also one of the trickiest things in conditional probability. So we're going to have to think very carefully about this. This is probably the most difficult item we're going to cover in class. Conceptually the most difficult item we're going to cover in class, at least in terms of probability and statistics.